Nature has a strict rule for heat. It always flows from warm areas into cold ones. To create a cool room on a hot day, you have to move against that current and force it back the other way. This is achieved through a closed loop of piping filled with a chemical refrigerant. This fluid acts as a vehicle, absorbing heat from the indoor air, carrying it through the system, and releasing it outside. For the refrigerant to move and dump that heat, it needs a driving force. This is the compressor. It takes in low-pressure, low-temperature vapor and compresses it, increasing pressure and temperature, turning it into a high-density gas capable of discharging heat. By manipulating these physical properties, the compressor provides the mechanical effort required to artificially lower the temperature of a space. In small-scale applications like a domestic refrigerator, the volume of heat to be moved is relatively low, allowing for simple mechanical designs. This is the reciprocating compressor. A piston moves inside a cylinder, pulling in refrigerant and crushing it into a high-pressure gas. Alternatively, small systems use a rotary compressor. A rotating roller pinches the refrigerant against the wall, achieving the same pressure with fewer parts. While these designs are effective for single rooms, they have inherent limitations. The back-and-forth motion of a piston creates significant noise and vibration and lacks capacity for larger buildings. While technically possible to cool a large building with hundreds of small pistons, the noise levels and maintenance logistics make it a non-viable engineering choice for commercial architecture. As cooling demands move toward commercial offices and VRF systems, the engineering focus shifts toward efficiency and quiet operation. The scroll compressor uses a different solution: two interlocking spiral scrolls. One remains stationary while the other orbits, continuously moving gas toward the center. This continuous motion eliminates the vibration of pistons, creating a smoother flow of refrigerant. These systems often utilize inverter technology, which allows the compressor motor to adjust its speed based on the cooling demand. Instead of a simple on-off cycle, the motor speeds up or slows down to maintain a precise temperature. Combining the smooth mechanics with variable speed motors provides the energy performance required for modern commercial buildings. At the highest end of the scale, such as in shopping malls, the volume of air to be cooled requires machines capable of high-capacity operation. Large-scale water chillers typically use screw compressors. These heavy-duty machines are built for industrial HVAC, offering long service life and continuous operation under high loads. Inside a screw compressor, two helical screws rotate against each other. As they turn, they trap refrigerant between the threads and move it along the length of the rotors, steadily increasing its pressure. The largest here is the centrifugal compressor. It replaces the physical squeeze of a piston with an impeller spinning at high speeds. This impeller accelerates the refrigerant outward, converting that velocity directly into the pressure needed to move it through the system. By shifting from a simple pump to high-speed velocity, engineers can scale a basic thermodynamic cycle to cool sprawling structures like international airports. These industrial systems operate under high internal pressures for months at a time. In a hospital, where temperature control is a safety requirement, these compressors are vulnerable to the wear caused by constant friction and heat. A common mechanical failure is known as liquid slugging. Because compressors are designed to handle vapor, any liquid refrigerant entering the chamber can impact the moving parts with enough force to shatter the internal valves. If the internal component seize, often due to a shortage of oil, the motor may experience a locked rotor. The motor attempts to turn the stalled mechanism, causing a spike in electrical current that can lead to a complete system shutdown. To avoid unplanned outages, technicians follow a strict maintenance schedule. This includes monitoring oil levels, tracking suction and discharge pressures, and tightening electrical terminals to ensure the motor operates within its design limits. While we often take climate control for granted, every cooled room depends on the steady, hidden mechanical act of a compressor circulating refrigerant.